Have you ever wondered what's really going on behind the scenes of our digital lives? Well, today, we're diving into the invisible math that powers our entire connected world. It's called stochastic analysis of communication networks, and it's the absolute magic that turns total digital chaos into the seamless connection you rely on every single second.
Okay, let's start with something we have all felt deep in our souls. Why does your super important video call freeze right when you're about to make your point? Or why does the finale of your favorite show start buffering right at the climax? It feels so random, so frustrating, and totally unpredictable.
Well, here's the thing. A lot of it is random. The real answer to all that digital frustration lies in taming this one incredibly powerful force, uncertainty. In any network, you've got data packets, user requests, even system failures, and they all happen at unpredictable times. So the goal isn't to get rid of randomness, because that's impossible. The real challenge is to manage it.
So how in the world do you manage chaos? Well, first, you have to describe it. In our first section, we're going to see how mathematicians and engineers literally create a blueprint for unpredictability itself.
And the main tool for doing that is something called a stochastic process. Now, I know it sounds really complex, but it's actually a pretty simple idea. It's just a way of mapping out a system that changes randomly over time. Think about the number of people logging into a website or the flow of data through a router. A stochastic process gives us the language to describe and, even predict the unpredictable. And there are different flavors of randomness, right? So we have different models for it. A Poisson process is great for modeling events that just happen at some random rate, kind of like phone calls hitting an old-school switchboard. Then you've got a Markov process. The best analogy is a frog on a lily pad. Where it jumps next only depends on the lily pad it's on right now, not the whole journey it took to get there. And finally, Brownian motion, which is just this continuous random wiggle, like watching a tiny speck of dust dancing in a sunbeam.
Let's really zero in on the difference between two of those big ones. On the left, you've got the Poisson process. See how it's made of sudden, distinct events? It's a path of jumps. But on the right, Brownian motion is this continuous, wandering movement. One is a hop, the other is a dance. And you have to know which type of randomness you're dealing with, because that's the very first step to getting it under control.
Okay, the next huge tool in our modeling toolkit is queuing theory. And I'll be honest, at first glance it sounds kind of boring, right? The mathematical study of waiting in lines. But trust me, you experience this constantly. From your email waiting to be sent to video data waiting to be processed, pretty much everything in the digital world is waiting in some kind of line.
Yup, you can just think of queuing theory as the science behind digital traffic jams. It lets engineers analyze the flow of all those data packets, predict how long they might have to wait in a line, and design systems that prevent a total gridlock. This is exactly what keeps your data moving smoothly instead of getting hopelessly stuck. So for our second section, we're going to move from just modeling the chaos to actually controlling it. Now that we have our mathematical blueprint, what's the action plan?
We have our map of unpredictability. So now the big question is, how do we navigate it? How do we actually steer the system to get the best performance, even when things are unbelievably busy and random? We need a strategy.
And one of the most powerful strategies out there is called heavy traffic analysis. This is the specialized tool engineers pull out when a network is under insane stress. We're talking a Black Friday sale or a video that's just gone viral. It helps them cook up smart, nearly perfect control rules for the most congested systems you can imagine.
The source material actually calls this process an axiomatic recipe. Here's how it works. First, you model the jammed-up system using those stochastic processes we talked about. Then you analyze how the system behaves when it's pushed to its absolute limit. Based on that, you develop a rule, a heuristic for managing the traffic, like maybe prioritizing certain types of data. And then comes the really clever part. You approximate. The perfect mathematical rule might be way too complicated for a router to calculate in a split second, so engineers create a simplified, practical version, a closed-form approximation that gives you almost all of the benefit with none of the delay.
But, a clever strategy isn't enough. Not by a long shot. In our third section, we'll see why we need mathematical proof that these systems are not just efficient, but that they're also provably stable and trustworthy.
And I mean, the stakes could not be higher. When we're talking about our financial transactions, our medical data, or critical infrastructure, we have to ask this question: how do we actually prove our digital world is safe? How do we know with mathematical certainty that it's going to work when we need it most? The answer, and the proof, it all starts with what are called axiomatic foundations.
Just think of these as the fundamental, unbreakable rules of probability. It's the mathematical bedrock. Every single model and every control strategy we build has to sit on this solid foundation, ensuring that if our starting assumptions are true, the whole thing is sound.
To actually perform these proofs, engineers use really powerful frameworks like these. For example, temporal logic is basically a language for reasoning about time. It's used to verify communication protocols, the rules of digital conversation, to make sure they don't have some fatal flaw like a digital deadlock where two systems just wait for each other forever. And frameworks like CSP are used to prove that systems where a million things are happening at once, what we call concurrent systems, will all interact correctly. This mathematical verification is how we literally build trust into our code.
And that brings us to our conclusion. In Section 4, we're going to see how this incredible, invisible engine of mathematics takes us all the way from utter chaos to a stable, reliable connection.
So this is the incredible journey we've just been on. We start in a sea of random, unpredictable events. We use these sophisticated models to create a map of it all. Then we use advanced analytics to come up with a navigation strategy. And finally, we use formal proofs to guarantee the whole system is safe. That transformation, from chaos to reliability, is the story of every single piece of data sent across the internet.
And that's the bottom line. This invisible engine, which is all part of a bigger field called systems theory and control, is what runs our modern world. It is the reason that streaming, video calls, online banking, and everything else we depend on are not just possible, but are actually so consistently reliable.
And this leaves us with one final and really crucial question. As we build a future that relies on instantaneous, flawless communication for things like self-driving cars or even remote surgery, our standard can't just be pretty reliable. It has to be provably safe with almost zero delays. So the great challenge ahead is this: how do we evolve these amazing mathematical tools to not just manage chaos, but to guarantee perfection in a world where there's just no room for error?